Hey kids, we are back again talking about today average versus instantaneous rates of change. And so just a little visualization here with a generic f of x curve here. And if you're talking about the average rate of change over a closed interval, it's really a pretty simple thing. You are really just talking about the slope from endpoint to endpoint on that, even though it's a curve and of course it doesn't have slope per se. That's why it's called the average rate of change. On average, you take the change in y over that interval and divide it by the change in x. And this is pretty relevant right now with what's going on with the pandemic and all the coronavirus. You look on TV every day, they're talking about the rates of change of the curve. And this would be akin to, say, when they're looking at, say, the 7-day average, which they keep tracking. And you'll see on the graph they have these little segments which represent the 7-day average. And that's what they're doing each day, taking it over the last 7 days. And graphically what that's doing is taking the slope between those two endpoints, and that kind of line connecting 2 points on a curve. You may recall this term from geometry, your favorite class, I know. When you have a line that connects 2 points on a circle, it is not tangent to it. It is what's called a secant line. Secant line, same secant that we talk about in trig. It comes from the word to cut in Latin. So that's what average rate of change is. It's always over an interval, and so if you're talking 2 points, hey, rate of change kind of means slope, and just do the slope between those two endpoints. If you're talking instantaneous rate of change, so at 1 point, that's what calculus was really all about, and that's what the definition of calculus is the study of change, and that at any given moment a curve has a different rate of change, and that is what the derivative was all about. So if you wanted the instantaneous rate of change at a particular value c, then you're talking about f prime of c. And so that that could be anywhere here. At that moment it's got a different rate of change, at that moment it's got a different rate of change. And if you're talking about to complete the analogy with the pandemic here, that would be like your daily, like on a single day, that rate of new positive tests or whatever you're measuring, as opposed to the 7-day average. Some days it's higher and some days maybe lower. You take a 7-day average maybe to give you a broader idea. And of course the instantaneous rate of change graphically, that's the slope of the tangent line. Okay, so secant 2 points versus tangent 1 point. Derivative versus classic algebra 1 slope. Okay, so applying this to a curve here just to be comfortable with these, to see an example with these calculations and this terminology. Find the average rate of change for this function over this interval from 1 to 9. We got the square root curve multiplied by 6. And so, of course, if you want the average rate of change, or as I abbreviate AROC, it's fairly acceptable to do that. You're just talking about the slope between 1 and 9 on this curve. So first thing you might want to do is, this is the setup you're looking for, f of 9 minus f of 1 over 9 minus 1, the slope between those two. If you like to get these values off to the side, that's fine. If you like to do it all in one big fraction, that's fine. But the f of 9 would be 6 times the square root of 9. The square root of 9 is 3. 3 times 6, 18. Minus f of 1, which would be the square root of 1, is 1 times 6, 6, all divided by 8. And so that's going to give you 12/8, which reduces to 3/2. That's the average rate of change, the AROC, over that interval. And if you like the visualization here, that's what we found there. That point was 9, 18, and this point was 1, 6. And we just found that the slope from there to there is 3/2. Now, let's find the instantaneous rate of change at each endpoint, so at 1 and at 9. And that means we want the derivative. So if f is 6 root t, or again in power rule format, that's 6t to the 1/2. Then our derivative is 1/2 times 6, which is 3. T to the subtract 1, and you get negative 1/2. Or if you like to rewrite that, that's 3 over t to the 1/2, or 3 over root t. So at 1, you plug 1 into that derivative. F prime of 1, notice the notation, hopefully you're getting conscientious about that. 3 over the square root of 1 is 3. And there we go. Just showing you that at that point, that curve is fairly steep. It's got a slope of 3 at that split second. The instantaneous rate of change at 9. Same derivative, just plugging 9 into there. So 3 over the square root of 9, and that's 3. 3 divided by 3 is 1. And you can see the curve is flattening out, and so that slope right there is going to be less than that. There's no particular significance here with this and this and this, these three values, but one thing that is noteworthy is that the average rate of change is not the average of the rates of change at the endpoints. To draw a parallel between speeds, your velocities and your average speed, this would be like at the beginning of a time interval, like if you passed under an easy pass and you were going 5 miles an hour, and then 5 minutes later, I clocked you and you were going 75 miles an hour. Doesn't mean your average speed over that whole time was the average of 5 and 75. You may have sped up very quickly to get up to close to 70, 75 and driven that the whole time, or who knows. But these are just snapshots of what you're doing at that moment. They don't necessarily tell you about what's going on here, nor does this average tell you that much about these endpoints. However, there is one little connection we can make here, and that's this. Find the t value, or the x value if you like, but this is in terms of t. Find the t value where the instantaneous rate of change is equal to the average rate of change. And this, we've talked about before, this idea with when we were deriving the derivative rule using limits, and those cables, those speed cables on the ground, the pneumatic road tubes, that as you bring them closer and closer together, your average rate of change is mirroring your instantaneous rate of change. And that's this idea that if I average a rate of change, or a speed of 3/2, then there must be some time in that interval where I actually traveled that speed, where I actually had that instantaneous rate of change. And that is something in calculus that you'll learn more about next year, called the mean value theorem, and it's always true as long as the graph has a couple of properties, which you'll talk about next year. And so it should be true on this one. There should be a time when my slope is perfectly 3/2. If my slope was 1 here, 3 here and 1 here, there should be somewhere in between where my slope is perfectly 3/2. Is it halfway between? I don't know. But to do this, we take our instantaneous rate of change, which is f prime of t, and I set it equal to that average rate of change, which is 3 over 2. I'm just saying, well, where is that derivative? 3 over root t equal to 3/2. You can actually see it's kind of a nice equation to solve here, because it's 3 over root t, 3 over 2. You're really talking about, well, where does root t equal 2? Or in other words, at t equals 4. So t equals 4, it's in between, but it's not perfectly in the middle. It's not the midpoint of 1 and 9. So again, you can't draw assumptions like that, only that it did happen somewhere. And here you go. So there's that. Now let's just see it from a different context here. Revisiting some physics ideas for you kids who've been taking that this year and loving it, I'm sure. But this draws some tighter connections between some things you've learned, and you'll continue to do more with it next year. There's a big, heavy overlap between physics and calculus. So velocity is, by definition, the rate of change of your position. Your feet per second, miles per hour. How fast is your position changing, essentially? So if your position of an object is represented by the function s of t, it could be anything, f of x, but it's often called s of t. And if you are talking about the average velocity, this is just another way of saying, well, that's the average, and this word, velocity, is rate of change. So this is the average rate of change of position. So this is really just the AROC of position. And if it's over this interval, again, these two endpoints here, then you're doing the slope on S of t between A and B. So S of B minus S of A over B minus A, right? And if you think position-wise, this would tell you how much your position has changed by. Maybe it's in miles, maybe it's in feet. And then you're dividing it by how much time has elapsed. So you're going to get a velocity type unit. Meters per second, feet per second, miles per hour, whatever it may be. But now, if you are asking for the instantaneous velocity at a split second, well, the instantaneous rate of change, the instantaneous, the IROC of S of t, now you're talking about the instantaneous rate of change on this curve. That is the derivative. And the derivative of position gives you the velocity function. This resulting function will actually give you the velocity of that object at any given moment. And I don't think you did that in physics class, really. In physics 1, they don't use any calculus or derivatives. But that's sort of the significance here. So here's kind of a classical problem you may have done in physics, algebra 1, even algebra 2, talking about an object in freefall. In this case, I took a little inspiration from Seinfeld. If you know that show, it's only 25 years old or so, but a classic nonetheless. Kramer is on a 96-foot high platform, and he throws a junior mint upward with an initial velocity of 80 feet per second, and the position of that object, that junior mint, is given by this function. You might, to notice a couple things. Here's your initial height. Here's your initial velocity when it leaves his hand, and it's positive, so it tells you he threw it upward. And this negative 16 is related to gravity. The constant acceleration of gravity is negative 32 feet per second. If this problem had been in meters, the metric system, meters per second, then this would be a negative 4.9 because the acceleration is negative 9.8, which you'll see kind of arrives when we do our velocity function in a moment. But here you get that basic parabola, which is why you may have done these in algebra 1 even. I mean, certain elements of it. What is the average velocity of this junior mint over the interval 0 to 2? Well, again, average velocity, but it's over an interval, means we don't use the derivative. We don't use the velocity function. That's for instantaneous velocity. Average velocity is the average rate of change of position. So that is S of 2 minus S of 0 over 2 minus 0. S of 2, that's, maybe something you want to get off to the side on your own. Or do it all in the fraction if you like, if you can keep it straight. We'll even bring in the calculator here. And you know what? I think I'll even bring the graph element into this, just to remind you of some of these things you can do on your graphing calculator. So I put the function in ahead of time. I did adjust my window to match, the constraints here. I went from 0 to 7 on the x-axis, and I went up to 220 on the y-axis because this thing starts at a height of 96 and goes up from there. So you can see there's that graph. I'm just going to use the trace feature here to remind you of the things you can do. And if I want to know what's the position, what's the y value at 2, I can just type 2 when the trace is on and hit enter. And the y value is 192, and it shows you you're right there, right about there on the curve, almost at the peak. So that's 192 minus S of 0. S of 0 is just 96 when you plug that in. You don't really need a calculator for that. And you get 192 minus 96 over 2. And so that's going to be, of course, 96 over 2. 192 minus 96 is 96 over 2. And that's going to be 48. And more importantly, what are the units of this? This is a word problem. That is feet per second, which should make sense from a velocity standpoint, that those units. But if you think about what you're doing within this fraction, the top measures how far its position changed from here to there. You know, we started at a height of 96, we went to 192. It's a change in position of 92, and it took 2 seconds to do it, so an average of 48 feet per second. What's the instantaneous velocity of the junior mint at 1 second, 2 seconds, 3 seconds? Okay, this is where you want the derivative. So the velocity function, v of t, would be s prime of t, and that would be, use our power rule here, it's beautiful, negative 32t plus 80. The constant 96 drops away. There's your negative 32, which comes from gravity, or if you were in meters per second, it would be negative 9.8, hopefully a familiar number. And the velocity at 1 second, you plug 1 into this, so negative 32 plus 80, hey, it's 48 feet per second. Hey, very nice, same as that. How about 2 seconds? V of 2, plug 2 in there, you get negative 64 plus 80. Negative 64 plus 80 is 16. Notice at that moment, a smaller, a lesser velocity. At 1, that slope of that tangent line was 48. At 2, that's positive 16, and that should make sense because it's going up, it's still on the way up, but it's starting to slow down, it's getting towards that peak, and then it's going to get 0, and then it's going to start to come down. So at 3 seconds, we plug in 3, you get negative 96. Negative 96 plus 80 is negative 16 feet per second, and there we go. That should be no surprise either that 3 is now on the other side of that vertex. It's now on the way down, and that's what the negative tells you about. It's negative 16 feet per second. And you've maybe been seeing, from time to time in these homework problems where it might say use a graphing utility, use the derivative feature. I'd like to show you that this can actually be done on the calculator too. If you want to know what is the slope at 1 or the derivative at 1, if you go to this second trace menu, the calculate menu, you'll see these things here. And if you look at item 6, there's the dy dx, the Leibniz derivative notation. And if I hit that, it doesn't bring you a prompt. It's actually waiting for you to type in x value though. So if you want the derivative at 1, I just have to type 1 and hit enter, and it shows you the derivative at that spot is 48, and it shows you where you are on the curve, so you can visualize it a little bit. If you want to know the derivative, second trace, item 6, dy dx at 2, 16. Second trace, 6 at 3, negative 16. So there is this capability, and you should know how to do it. It's very cool. And I'll even show you while we're at it, there's a way to do it on the home screen as well. So if you hit math, it's where a lot of random things are, your cube root button, and you scroll down, there's that feature right above the summation and the log base button that you've used. There's the end derivative feature. If you bring that up, it brings this notation up on the home screen, and you can hit, I'm doing my derivative with respect to x of what? And again, there's the operational notation, derivative of what with respect to x. And you can actually type the equation itself. I can type this in there, or you could actually say, I've already put it in y1, I've stored it in y1, I could just put y1 here. And y1, that notation is in the F4, so it's that's green, so I've got to hit alpha trace y1, and then at what x value, that's what that bar is showing you. It's like saying, plugging what number into that derivative. And if you want it at, for example, 3, notice it gives you that negative 16. So kind of some cool things to play around with as you're doing these things, but you'll definitely see a lot more of this next year, but good to know what's in there. For right now though, they really are stuff you can do by hand. And part C, what's the velocity at the moment it hits the ground? And I don't mean like it's zero because it hit the ground and it stopped. I mean at the moment upon impact, like what velocity does it strike the ground with? And the first thing you got to know is, well, I have this velocity function and it works as long as I know the time. I can plug that time in and get it out. I got to know, well, what's the time when it hits the ground first? And if you figure out that time, then I can plug that time in and get its velocity. So it's really a two-part problem. So first I've got to say, well, when does my position equal 0? And when does my height equal 0? So I go to my function here because I'm really saying I'm trying to find the time when this is 0. You're finding the x-intercept. And of course, you could do this on the calculator also with the intersect feature, with the 0 feature. We'll do some good old-fashioned factoring though. You can factor out -16, and you'll have minus 5t minus 6 there. Continue to factor that. The -16 is kind of irrelevant because it's a constant. -6 plus 1. Our two solutions are +6 and -1. Obviously, we're not talking about this. This is the time that it requires to hit the ground. That seems about right. If this was about 3 seconds on the graph, then 6 seconds should be there. It was nice that it worked out perfectly on the dot, no decimal. And now what's the velocity at that moment? The velocity at 6 is -32 times 6 plus 80. So that's going to be -192 plus 80, which would be -112. Yes? Feet per second, of course, got to always label. There are units to be had, and of course, a nice way to check yourself here. Trace 6, if you want to first make sure, yes, that is the y-intercept. Second, trace dy dx at 6, -112. Boom, got it. So, sorry this video ended up being a little bit longer than normal, but there's a lot of little ideas that you can unpack and connect here with things you've done in physics and things you've done in Algebra 1 and things we've done with limits and rates of change. So, hopefully this tied together some ideas for you. If, as always, got any questions, just hit me up and keep working hard, kids.